Okay, now we will begin discussing the principle of inclusion-exclusion. And so I'll discuss the general perspective of when you would use this technique. You use this technique whenever you have some sort of counting problem where you're trying to count the size of some set A that's a subset of a larger set, and a larger set you know how to count. And moreover, you know that A avoids a bunch of other subsets that are the properties you don't want. For instance, the property that a certain child gets too many pies, or the property that some permutation has a fixed point. So usually you have some sort of counting problem where you're trying to avoid a bunch of configurations, and you're able to group the possible configurations as other subsets, A1 through AK. And the thing you're actually interested in is disjoint from all of them, but the set X is the union of all of them. And of course, unfortunately, when you've got X as a union of a bunch of sets, you can't guarantee that these other sets aren't overlapping, and so it turns out that you have to consider the intersections. And you can prove that the size of the set you're interested in is actually equal to this summation. And so it's worth noting this formula is not in the book, because the book tries to avoid summation notation at this point. But if you're using summation notation, you can write it down this way. So it's worth noting the summation is over all subsets of the integers 1 through k. -1 to the size of this subset times the size of this intersection, which is the intersection of the corresponding sets coming from S. And so on the next slide I will actually do an example, but I've done an example before. And it's worth noting, in order to interpret this formula properly, the intersection corresponding to this empty set, which is an option, is interpreted to be the whole set X. This guarantees that every element appears at least once, otherwise this formula is false. And in practice, this theorem, this principle of inclusion-exclusion, is used whenever these intersections are easy to compute. So sometimes it turns out the problem you're interested in solving is hard to compute, but you can write it as an alternating sum of things that are easy to compute. And we've already seen a few examples of that. And so as an example of this formula at work, suppose k is 1. In the case that k is 1, there's only one subset A1 that you're trying to avoid. And so there's only two possible subsets of the integers 1 through 1. Either the empty set, which corresponds to this term, or the set containing the element 1, which corresponds to this term. And since that set has size 1, we see a minus sign. And this tells you the obvious thing, that the way to count the number of elements is to count the total number of elements and then throw out the ones that aren't in the subset you're interested in. Now what happens when k equals 2? Well, this is the theorem similar to the formula we had seen earlier about the size of the union of two sets. So here we've got, there's 4 subsets of the numbers 1 and 2. There's the empty set that corresponds to this term, and the 2 singleton sets in the whole. In fact, here I decided I'd go ahead and make it explicit. You've got 4 possible terms. These sets have size 1, so you see minus signs. This set has size 2, and so you see plus sign. You see 1 and 2, and so that's the intersection you're taking. That the intersection of a singleton set's just the set A1, the set A2, and so you see that this formula works. In order to count the elements that aren't in either of these two sets, you take the whole set, you throw away A1. So we throw away the things that were in A1 and the things that were in A2, but there was a common intersection, so we add those points back in. And so we've thrown away everything in this union exactly once, and so we're left with everything that's outside. On the other hand, if we have 3 subsets we're avoiding, so we want to be outside all 3 of them, then we have to throw away A1, A2, and A3. But then we see that we've thrown away the things in their intersection too many times, so we add those back in. But then something in the triple intersection was removed 3 times and added back in 3 times, and so we need to remove it 1 more time, and that's part of the reason what makes this theorem true. And so we see there were, in this case, there 8 possible inner subsets of 3 correspond to 8 possible intersections, and we see 8 terms with the appropriate signs. And that's how the formula works in general. For a given k, you can actually write it out longhand. Oftentimes it's actually very hard to write, though, as k gets bigger. So as one application of inclusion-exclusion, we're going to do the hat check problem. So traditionally the hat check problem is that n people show up at a restaurant and check in their hats, and at the end of the night the waiter accidentally mixes up the tags and everyone gets the wrong hat. They don't get their own hat back. And the question is, how many ways could the waiter have made this mistake? So using set theory notation, we let x be the hat distributions, the set of ways people get their hats or get hats back at the end of the night. And we're interested in this subset A, which are the hat distributions where no one actually gets the correct hat back. It's worth pointing out we're assuming that everyone's hat is somehow distinct. And we see that we can divide up the hat distributions into other subsets. For a given person I, we can let AI be the hat distributions where I actually got their hat back. And it's worth pointing out in this case that AI and AJ are definitely not empty, because this would be the set of hat distributions where both I and J got their hat back. But certainly A intersect AI is empty, because A are the set of hat distributions where no one gets their hat back. And so we see that we can apply the principle of inclusion-exclusion, which immediately tells us that the answer should be this summation over all subsets of n, -1 to the s, times this intersection. So the challenge, of course, is to compute this intersection. Can we do it? And what do we see? We see that, what is this intersection of all these sets? Well, it has to be the hat distributions where I gets their hat for all I and s. So everybody who's in this subset S gets their own hat back. It's worth pointing out that this does not tell us anything about the people who aren't in S. The people who aren't in S might get their hat back, or they might not. It depends on the distribution. So the size of this intersection, I claim, is the factorial given by n minus the size of S. And how do we see this? Well, consider the set of people who aren't in S. Let's order them T1 through Tn minus S in increasing order. Then we know that T1 gets one of the remaining hats. We know the people in S get their own hat back. We know T1 gets one of the remaining hats. We don't know which one, so there's n minus S ways it could happen. After that, we know T2 gets one of the remaining hats, but he can't get the same one as T1, so he has to get a different one, so we subtract 1. Similarly, we've now removed 2 hats from the pile, so T3 gets n minus S minus 2 hats, and so on and so forth. And by the time we get to the last person, there's only 1 hat left. And since each of these choices, the dependency on the choices is already taken care of by doing the subtraction, we get a factorial. This is also known as choosing a bijection. And it's interesting that it doesn't depend on S itself, just the size of S. And so it turns out that this will actually simplify our formula in a moment. And so we apply the principle of inclusion-exclusion. Then we apply the formula we just found. And so we get that the number of ways nobody gets their hat back is this summation over all subsets times this of this terrible looking formula. And well, there's exponentially many terms in general, but we could actually simplify the formula by noting that since this term only depends on the size of S, then we could actually try to rewrite this as a double summation over all the possible sizes of subsets, then summing over all subsets of that possible size. So summing over all k, and then all subsets of size k. And then since the size is k, we can replace these two terms with k. And then we see that this term is constant over this entire summation. It only depends on k, it no longer depends on S. And so, since it's a constant, a summation of a constant arbitrarily many times is just that constant times the number of terms in the sum. and the number of subsets of a given size is a binomial coefficient. And so you can actually sometimes in general replace this really complicated formula with something that looks a little simpler. This now only has n terms in it, and you can actually calculate it pretty quickly. It's worth pointing out that the binomial coefficient has an n minus k factorial in the denominator, so you could actually simplify this a step further if you want, but I'm not going to. I'm going to go ahead and call this the answer, because it turns out in general this is actually the best known formula for this problem, and it actually solves the problem. And this is actually the derangement problem. I'm calling it hat check, but you could also do this with permutations, gifts, and all sorts of other things. It's cases where you're rearranging something such that nobody gets the thing they started with. And in general, this is the nicest formula we have. So now we will give another application that's related to the last investigate activity of the section, counting surjective functions. Since I'm using the general formula, of principle of inclusion exclusion, I'll actually give us the general formula for the number of surjective functions. So fix n and k. We want to count all surjective functions with domain the integers 1 through n and codomain the integers 1 through k. And in case you needed a reminder, a function is onto or surjective if for every element in the codomain there's something in the preimage. Which of course means that what we really want to do is avoid the set of cases where you've got a function that doesn't have that in the preimage. So we're trying to avoid these sets of functions where one of the preimages is empty. Fix one of these elements in the codomain I, and look at the set of functions where the preimage under that map is empty. So then we check our conditions for the principle of inclusion exclusion. We see that every function has to lie in one of these sets. Either it's onto or one of these preimages, at least one of these preimages is empty. And moreover, if it's onto, then the preimages can't be empty, so these sets, the intersection of the set we're interested in one of these forbidden sets is the empty set. And so by the principle of inclusion exclusion, the number of surjective functions is given by this summation. Notice here that the summations over all subsets of k, all subsets of the codomain. And so we are done if we can figure out a nice formula for the intersection, which I will do on the next slide. So we study this intersection in stages. What does this intersection mean? It's the set of all functions where the preimage of I is the empty set for all Li in the set S. Of course, from the point of view of definitions of functions, that's the same thing as saying that the range of the function is a subset of this set difference. In other words, the function values have to take on values between 1 and k that aren't in S, because otherwise this preimage would be non-empty. But that's essentially the same thing as specifying a function whose codomain is in the set difference. So again, like the hat check problem, this isn't guaranteeing that this function here is onto its codomain. It's just guaranteeing that it's definitely avoiding the set S. But of course, we know now that we're just dealing with an arbitrary function between two finite sets, and so we know how many there are because we studied that problem before. That is an exponential, the size of the codomain, to the size of the domain, which in this case is n. And why was that? Because for every input, we have to specify a possible output, and that's the set number of possible outputs we have to choose from, and the choices are independent, so by the product principle, we end up multiplying this by itself n times, so that's a power, which in this case becomes k minus the size of S to the nth power, because that's the size of this set difference. And so now we know our formula is going to be this summation, powers of s, alternating powers of s, as we sum over all subsets of the integers 1 through k, times this intersection term, which is k minus the size of s to the n. Again, as we saw with the derangement problem, the answer does not actually depend on s itself. The terms don't depend on s, but on its size. So we can do this double summation trick again. And doing this double summation trick, we sum over all possible sizes of subsets. Then we sum over all subsets of that size. So the sizes can only range from 0 to k. And fixing a size I, we sum over all subsets with that size. We have this formula, but now we can replace s with I. And now we see that this term does not depend on s, it only depends on I. And so we're summing a constant, binomial coefficient many times, so we can replace the summation with the binomial coefficient, and we get this as our answer. And again, it turns out in general this is the best known formula. And at the beginning of the problem, n and k were parameters, and we see they are in the final answer. Here, the k is in the summation, it's in the binomial coefficient, it's right here, and the n is in this power. And so now, if you ever have to figure out how many surjective functions there are between two finite sets, you just plug in the sizes of the sets into this formula and you get your answer. So as a case, one of the examples in the book, they actually do the argument I just gave in the special case where n is 5 and k is 3. And so if you apply the formula we just had, you get this summation. And if you expand the summation out by varying I, you get 4 terms. And then if you simplify the coefficients, you get 3 to the 5th minus 3 times 2 to the 4th plus 3 times 1 to the 5th minus 0. And from first principles, you could have gotten this by noting that this is all possible functions. And here you're subtracting off the functions where you pick one of the elements in the codomain and decide not to put that in the image. So there's 3 possible choices. And then what's left over has to be a function from, oops, see, here's a typo. That should be a 5. From the numbers 1 through 5 to the other 2 numbers in your codomain. There's 2 left over, and so you have all possible functions. But then you could also consider the ways that you missed 2 elements in the codomain, which means in this case there's 3 elements. So you pick the one element that is in the image, and there's only one function that can map to that element, so you get a 3. And it turns out if you check this formula, this last term is always 0, corresponding, of course, to the fact that you can't really write a function from a non-empty set to an empty set. And so that does give you an answer. And if you work out the arithmetic, as you see, you will get exactly 150 functions. So there are 150 surjective functions. As another silly case, it's worth pointing out that when n and k are the same, you would actually probably avoid doing inclusion-exclusion, because it turns out if you have a surjection between 2 sets of the same size, the function has to be a bijection in this case, right? Because every element gets mapped to, and it turns out the size of each image, pre-image, has to be exactly 1, because if you have 2 points mapping to the same codomain point by size considerations, things end up not working out. So the answer is actually simpler in that case. So you could actually try that, do the calculations the hard way, and see that you actually get n factorial.